Now we're starting chapter 2. Chapter 2, this is where the rubber really hits the road as far as calculus is concerned. All right, there are two big areas of calculus that we are going to be dealing with in the next two chapters. This one deals with slope analysis. And as you recall, the limits dealt with both slopes and areas or whatever was associated with that. We're dealing with the slopes in this chapter. Now, we're going to refresh our memories as to A, how we find slopes in algebra, particularly algebra 1, maybe a little geometry, and 2, getting back to understanding that we're trying to find infinitesimal differences by using large differences as the starting point, and then understanding how the infinitesimal distances are going to give us actual slopes, not approximated slopes, like we will with the large distances. So I have a point C. All right, that is the point of X. Now that point then on the y-axis is going to be f of C, which is y. We have to keep thinking in terms of, but since we're dealing with functions here, we've really got to think in terms of that instead of that. But if you, in the back of your mind when we're talking about slopes and you're thinking of delta y over delta x, then it's delta fc over c, delta c. So, and you'll see what I mean as we get through this. So let's suppose that we go over a certain amount of distance forward on the x-axis to the point where we now have a a second point that is going to be slightly away from the original point. We're making a big spacious difference so you can see what we're talking about, but imagine this as being two consecutive points. Okay? Now when we do that, we have now changed the distance by delta x. It's changed x. So this point right here then becomes c plus delta x. That minimal change we call delta x is to be added to the c. That means then that this y value of the point is going to be function of c plus delta x, whatever that turns out to be, which we will now call y2. This will be y1. We'll consider this x1, and we'll consider this x2. So when we find the slope of this resultant tangent right here, and again, imagine this is just being consecutive, there's no space between them, but this is part of the theoretical approximation that we're using that is actually all that approximate. It's going to be exactly that. It's going to be actually overlapping the same as that, but because we've got some space, you see that gap of the curve going in there. So when we calculate the slope, which we know is delta y over delta x, which of course means it's going to be y2 minus y1 over x2 minus x1. Then we plug in these values for y2, y1, x2, x1, we get the function of c plus delta x minus y1, which is the function of c over the change in x. Well, the change in x we've identified as delta x. So that's going to be delta x right there. And this is the definition of terms of functional values. So if we can figure out a way to make this delta x approach 0, because they're going to be right on top of each other, so it's basically 0 for all practical purposes, this is going to be giving us exactly, not approximately, exactly the slope at any point on a curve. By using manipulation of algebra in functions, you'll see what I mean by that. Okay? So let's start with a very simple one. Let's start with a linear function, a straight line function. Let's say that the f of x is equal to 2x minus 3. And again, remember that is the y value. But we're not going to write that down. We're going to think it, but that is not going to be expressed on the board here. And we want to know what is the slope of this line at the point 2, 1. So we use the definition that we just came up with. That is the limit as delta x approaches 0. And I believe I may have forgotten to put that in there, so we probably should have. That should have a limit as x approaches 0 to show that it's infinitesimally different between each other. So make sure you put the limit in there. But I'll put it right here, so that'll be absolutely correct. The limit as x approaches 0 of f of c plus delta x minus f of c over delta x. That is our definition. This is the one you should have instead of what I put up there. You got the limit. That's really important. Okay? So, if f of x is 2x minus 3, then we're going to put in the equation for that over here. So I'm going to keep putting limit as x approaches 0 for this. Okay, so the function is going to be 2. Now this is our x value that we're going to plug in right here. Okay, we're going to plug this whole thing for x for this particular point, because that's what we do with functions. That'll be x of, if that was function of 5, we put a 5 in for x. If it was f of 100, you put 100 in for x. But instead of numbers, we've got the expression c plus delta x. So I'm going to plug in that for this equation. So this is going to be 2, instead of 2x minus 3, I'm going to be putting in c plus delta x minus 3. So that is what that is going to be right there for this part right here. Minus, then f of c is just going to be then 2x plus 3. Or I mean 2c rather. So this is going to be 2c minus 3. We're plugging the c for the x, and we get 2c minus 3. Put that in parentheses over delta x. So you can see how this can be a bit confusing. You got to remember that the parenthesis here describes what the x is going to be replaced with when we do our functions. Okay? So it will probably help to go real slow to start off with until you get in the habit of doing this. So this is exactly what we did. Now we got some resolution, algebraically speaking, to do here. So when we do this, we distribute the 2 across this, and get 2c plus 2 delta x minus 3 minus 2c, and that changes the sign here with plus 3. Well, and this is all over delta x. Now notice what happens here. 2c and negative 2c cancel out. Negative 3 and positive 3 cancel out. So that leaves us 2 delta x over delta x, which is equal to 2. So we are saying that our slope equals 2. Now, let's go back in time and remember what y equals mx plus b means. I think this gets lost, particularly when you're learning a whole bunch of new stuff and you really don't know what this means and you're afraid to ask questions, so you just go along with it, and you kind of get, you kind of understand the trick that's involved, but you don't really understand the process. You just are performing monkeys, and you're coming up with an answer, and yay me, I got an answer, but I don't know what it means. So let's make sure we understand what it means. Okay? When you take a look at this, you understand that this is the equation for a straight line. When your exponent of your x is 1, it's called a first degree equation. When your exponent is 1, it's going to be a straight line. And whatever number is multiplying your x will be your slope. Right? Remember that? So let's go back to the very beginning and look at the equation that we're dealing with. We know that this is y equals 2x minus 3. What's the number multiplying x? 2. That is our slope. So we didn't really have to go through all that, because if we had recognized that this is a straight line, of course it's 2. But we had to prove it algebraically to show that that is indeed what happens no matter what point we pick on there, whether it's one a mile away on that line or one smack right next to it. It's the same. Okay? Now, that's not why calculus was developed. It is the basis for it. It's the understanding that that is ultimately what you're trying to do, is find two consecutive points that form a straight line, and you can come up with that kind of situation. But two consecutive points are impossible to know unless you're dealing with limits. And that's why we spent an entire chapter on this, what seemed to be an arbitrary concept called limits. And we're playing the game again. Okay, performing monkey time. I can do some algebra. What does this mean? You're finding out.